The last section, experimental evidence to support the general theory of relativity. We need to outline an experiment that provides evidence for gravitational redshift. If you remember, low clocks go slow, high clocks go faster. It also means that a time period here, when it gets to the top, will actually be observed to be slow. So they observe the clock from the bottom, they see it as going slow, and it does go slower. So let's say we have another way of looking at it is gravitational redshift. If you have a light source which is low down in the gravitational field, and the light goes up, it loses energy, E is equal to HF, it loses frequency as well. It will become shifted towards the red part of the spectrum. The wavelength will get longer. We have to outline an experiment which provides evidence for this. Now, in the height of a building, this is going to be so slight, it is barely observable. But using one method, we can actually prove that this is the case. And it's known as the Pound-Repka experiment. You know that when an atom does this transition from an excited state to a base state, it steps down in the energy level, and a photon is emitted. So, and it emits a photon. This photon is given an energy, E is equal to HF. When that same atom in its base state encounters the same photon, it will absorb that photon and go back to the excited state, but only if it's the same photon, the same size photon, the same frequency. Then that same frequency will cause an excitation. If the photon's frequency and therefore energy is different by even a slight amount, then it's either going to be too much for this energy change or too little, so there will not be an energy transition. So the atom won't be able to absorb it if there's a slight change in the frequency. Now, when the photon travels through a gravitational field, its frequency and therefore its energy will change due to the gravitational redshift. So this light is going to go from the bottom of the tower to the top of the tower. It will become slightly redshifted. This means the frequency will be slightly changed, which means that the receiving atom can no longer absorb it because it is not going to have enough energy to facilitate this energy transition. So how can you cancel out gravitational redshift? What you could do is by counteracting it with a Doppler effect, by either moving the receiver towards the light source or move the light source upwards. Then you're going to counteract this effect by using the Doppler effect. So Pound-Repka countered the gravitational blue shift or redshift, or blue shift, so the light is coming down, by moving the emitter away from the receiver. Okay, this is going in the opposite direction, so it goes from as the light goes down, it becomes bluer. So basically, if the emitter is moving upwards as it transmits the light, then you're going to counteract for this gravitational blue shift. And you counteract it by using a relativistic Doppler redshift by the same amount, and therefore the energy released will be equal to the frequency of the photon released will be equal to the frequency of the photon received. Also, we need to outline an experiment for the bending of electromagnetic waves by a massive object. Well, this can only happen in space, and I've mentioned this already. This is the observer on Earth looking at 3 stars. When the sun is in the way, this third star appears to be in this position because the light is bending around there. It basically bends round. Light travels in the straightest line possible, but 4-dimensional space-time is curving around the sun. That light tries to follow this shortest path, the geodesic, along the 4-dimensional curved space-time. This was noticed in 1919 by Sir Arthur Eddington, who measured the deflection of light near the sun during a total solar eclipse. The results supported Einstein's general theory of relativity. Now we have to look at gravitational lensing, which is the same effect but in a more exaggerated sense. Gravitational lensing is the bending of light around a massive astronomical object, and what happens is that you produce multiple images or magnified images of a region of space that is further away. We have 4 videos that you can watch, where I will put a link at the end of the next few slides. Here's an example. The light from this distant star is travelling in this direction and this direction. However, near this large gravitational object in the way, the 4-dimensional space-time gets distorted, so the light will bend around there and bend around there. The observer on Earth sees the light coming from this direction, so it looks as if there's an image here, there's an object is here. It also looks like the light has come from here. So by having this large gravitational object in the middle, it appears that there's one source here and there's one source here, which are actually coming from the same star, which is on the other side of this object here. So we get multiple images of this star. And here we have again, we have a galaxy in the middle here, we have a distant light source. The light bends around due to the curvature of space-time. And so the observer on the Earth is going to see what is basically a banana shape image here and a banana shape image here. And of course these are both images of the same light source. And what one would see due to gravitational lensing, this is a large gravitational object. There's an image here, an image here. These are both images of the same light source, which will be on the other side of this large gravitational object here. And here we have the same thing again. We have multiple images here, 2 images around here. This is like a banana-shaped image here, and often we get these squashed images, which are these banana shapes, images of a distant light source, where the light is bending around a large gravitational object, and it acts a bit like a lens. So it's called gravitational lensing. Here we see lots of distant galaxies and see these banana-shaped images around there, 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 there. All these squashed images are images not of bananas, but of distant light sources, where the light is following a different path because it's been distorted around a large gravitational object. And this is the end of the relativity topic. I have a couple of videos that you could watch. If you go to this URL, this takes you to a playlist where there are 4 further videos of gravitational lensing, where it's shown in a much more interesting way. So there you have it. That's the end. I hope these videos were useful to you. Good luck in your exams.